Good afternoon. Normally, I'd start by talking about last week's practice exercise, but because we have a guest speaker at 4:30, I just want to make sure all the material is covered before then. So if we have space after we're done talking about the material, then we'll talk about the practice exercises. But they were really well done this week. I think it was the best they've been done so far in the course before, all the people who didn't do them. Those marks are put in. So, yeah, great job with sociolinguistics. So I'll talk about that after. So this week is computational linguistics, and there are so many different ways that we could do this lecture. Computational linguistics is incredibly vast. From a computing science perspective, you can go into like the nitty gritty details of the mathematics and code of how computers like process sounds internally and process words and tag words for part of speech and meaning and like do all of the things inside the computer. And that's a very mathematical way of doing things. Um, we could take a look at what the computers are doing, but just sort of brush over the mathematics and talk about it from like a higher level. Like say, okay, well, here's how the parts of speech are being assigned, and just sort of like skip over that math. So we're going to do a little bit of that, but we can also talk about some of the applications of computational linguistics. So how people interact with machines and technology that use language. So instead of just picking one of these different styles of doing this lecture and spending all that time on applications or all the time on talking about high level computer um, code or whatever. We're going to spend like a very, very, very small amount on the mathematics just so you know what some of it is like. We're not going to actually go through it. We're going to take a look at what the computer is doing at like a higher level, brushing over the math, and then we're going to take a look at some applications, some of the things that we interact with on a daily basis that uses language. So, if you are interested in computational linguistics, there are so many different things that you can do. So, if you really like coding, there's an area in computational linguistics for you. If you're more of the language side or the language learning side, you don't actually need that much coding knowledge, and you can still be a computational linguist, which is um, maybe not expected. But you still have to learn a little bit, but you don't have to use it as much as like computing scientists use it. So computational linguistics is very general. It's just about how computers analyze, process, and interact with language, but it's also about how humans interact with technology that use language. So there are many different domains. So you can talk about the phonetic side. So um, one of the first things we're going to talk about today is about speech. So when we talk, we're producing sounds and our ears are picking them up. But computers don't have ears. Computers don't have brains. But somehow, when we speak, if you have the subtitles on in Zoom, somehow the computer is picking up my voice and turning it into words live as I talk. And somehow the computer does an absolute fantastic job at converting my words into text. In fact, as I've said these last sentences, I've been staring at the text as it's been converting my words into text, and it has not made a single mistake. And that is incredible. But that did not happen 15 years ago. So that's one side of computational linguistics. Another side that's very important is part of speech and sentence structure. That's doing it at the same time. So as it's converting my sounds into words, it's also building sentences. So there's the syntax part of it as well. Computational linguists might not be building that kind of stuff. They might just be looking at large databases of language, and they might just be trying to find patterns, trying to develop the field. So they could be working on the theoretical aspects of language, trying to develop linguistic theory and help linguists find patterns that might be really difficult to find. without having the ability to analyze like really, really, really large sets of data. Humans are not good at looking at thousands and thousands and thousands of sentences at one time, but computers can do that because computers aren't limited by the memory capacity that humans have or by attentional capacities that humans have. With computers, you just, you know, give it some more RAM, give it some more processing power, give it some more storage space. Humans, you can't just like change something out in our brain and give ourselves some more memory to work with or more attention. We can't do that. Uh, we have some applications too. So in terms of media, translation is huge. This has not been perfected. If you've used Google Translate and you try to translate a sentence from one language into another, uh, but machine translation can be incredibly helpful. If you have like a movie script that you need to convert from one language to another, or subtitles in a movie to make it accessible to other languages, um, automatic translation or machine translation can assist humans. Or if it's good enough, it can do it entirely. And humans can kind of fill in the rest mentally when things are odd. I'm sure you've all downloaded movies or seen videos online where there's just a really weird translation, and you're like, "Hold on, this isn't quite right." And it's probably done by either a learner of the language that doesn't quite get the grammar, or it's done by a computer that isn't quite perfect. Um, Another application are things like assisted language learning, which we'll talk about later, and also just chatbots. So sometimes, especially when you're on the phone and you're talking to some of these service agents and you're like, who do you want to talk to? And they don't have the button menus and you have to actually talk to them over the phone, and how awful some of those are. Uh, Online, when you type, they're usually a little bit better because they're not dealing with sounds, they're dealing with words. But some of those are pretty good, some of those are pretty bad. And we'll take a look at the different types of chatbots they are, and maybe that'll explain why some chatbots are so terrible and some chatbots are a little bit better. But yeah, there's a lot of things in computational linguistics that you can do. And one computational linguist doesn't do all of these things. There's simply too much. So here's the nasty slide with the mathematics. And we're not doing any of this, but just to show you behind the scenes of like when someone is trying to figure out like what is a sound that it's being given, or what is a part of speech that it's trying to determine. There's a lot of mathematics that go on behind the scenes, and this isn't like the most modern method, but this is like an somewhat modern method that uses a lot of probability. So if it's like making a prediction of what's coming next and you're trying to figure out the category, it might look at the previous word in the sentence and say, well, if I have the word I and I'm trying to figure out what the next word is going to be, well, I'll take a look at all the words I've ever seen before in a corpus, and compute the probabilities or occurrences of those happening. So you can create like charts with probabilities for words. Then you can apply these functions to smooth things out, so that way there's no zero probabilities, so that way there's some randomness associated with it. And like this is the stuff that goes on behind the scenes, and this is like far too advanced for a course that isn't in computing science. So this is one side of computational linguistics that we're not focusing on, but this is certainly a big part of it that makes all the systems work. So um, if we do any math, we're doing things like really basic addition. We'll see a little bit of that, but um, a lot of computational linguistics in terms of understanding sounds and words is probability. So the computational linguistics really is computing science and linguistics put together. So, linguistic information is used to inform a lot of the statistics that goes on. And statistics is used to help figure out a lot of the um, ambiguities in linguistics. So we'll see this in a few slides as well, but there are a lot of words that can be multiple categories or words that have multiple meanings. And if you're a human, it's a lot easier to figure out based on context what that is because you understand meaning. But computers don't understand words. Computers just get information. They don't really know what meaning is. All they have are, probabilities that they can work with, data. So humans, we can think about things. We understand meanings. Computers just have to use numbers. So let's start with speech sounds. And when we talked about speech earlier in the semester, we focused on like how the mouth makes sounds. So we talked about like the glottis with voice and voiceless sounds. We talked about consonant production. But how does a computer understand these? Well, when we produce sound, we produce these waveforms. So what this waveform is showing is like a difference in air pressure. So the air pressure is coming like when we come from the throat. So when the glottis opens and air is released, we get this difference in air pressure as it comes through our mouth. And this is being recorded in this wavelength. So we have these peaks in our waves. So this is the very top. We have a couple terms just so you're familiar. The difference between sort of the resting point, which is 0, and the peak is what's called the amplitude of the wave. So this is basically how high the wave gets. So, I mean, this is one of the main terms that we're going to need for acoustic waveforms. And the distance between two peaks is going to tell you basically the frequency. The frequency in hertz for some of these waves. So we'll see how this is shown in some of the graphs later. So basically, how many cycles per second will these sounds have? So we're not going to actually be computing individual waves for this, but just when we see another graph later, you'll know what you're looking at when you see terms like amplitude and frequency. So this is what's being produced. Now, obviously, if we don't have computers, we would not know how to visualize this. But this is information that a computer is picking up through a microphone. So does the 0 line mean no air? This is just a baseline, so like standard air pressure. So yeah, we could just say like this is like regular air pressure. So that's why it can go negative and positive. Okay. So in a waveform, we also get other bits of information, like the pitch of your voice. So the pitch of your voice, as a reminder, is how low your voice gets or how high your voice gets. You also get information about loudness, and this is called intensity. So intensity being very quiet or intensity being more loud, so you can tell the difference between those two. And a computer can extract the information from the sound waves when it gets information about your voice, and it can track these. So on the left here, with the waveform, here's 3 o'clock. I'm going to actually zoom in on this so we can see this a little bit better. So here's 3 o'clock, 3 o'clock, 3 o'clock. You can actually hear when I say 3 o'clock that my pitch at the end of 3 o'clock is going up. And this is what this little track represents when it goes up at the end. 3 o'clock, it rises. So this is the pitch of what I'm saying. So the pitch is tracked by the computer, which is good information. If the computer wants to record all this information and produce my voice again, it needs information about pitch. Otherwise, it would just get a monotone recording, right? It also records information about loudness. So if we take a look on the right, here's a different sentence. Is it a long movie? Is it a long movie? Is it a long movie? We can see here that this is the loudness or intensity track in the middle. So is it a long movie? The very beginning and the very end of the sentence or question is quite quiet, and it gets louder, especially in the middle of the long vowel. Is it a long movie? And even when you ask that question long, usually spend a little bit more time producing that vowel, long, which is why it gets louder. And then when you start to end the question, is it a long movie? Usually at the end of a question, you start to taper off, of course. When you stop speaking, you get quieter towards the end of your sentence, which is why we see this drop off at the end. And we can also see the intensity of a sound based on how high our amplitudes are in these waveforms. So of course, when the amplitudes are really high here, the waveform is big, we get very high intensity. So these little bumps here correspond with new peaks in the intensity wave. And of course, when it gets quite small, we see like a little dip in our intensity wave. So again, like we're not really talking about necessarily how computers can do this, but just what computers can do. So computers are able to get the pitch and intensity tracks for our audio. Well, at least this is just the basics of speech sounds at this point. Okay. So it takes this information about a waveform and it converts it into what's called a spectrogram. So this is different than what you've seen before, probably. But for phoneticians and linguists, this is more informative than a waveform for us, because this gives specific information about the speech sounds. So what this shows, and this is very hard to decode if you haven't done phonetics, and we're not decoding what this is in this course, because that's just, it's difficult. It requires weeks and weeks of training. So these little black bars tell us which frequencies have high amplitudes, or which frequencies are like more intense than others, to put it as simply as I can. And different vowels and different consonants have different frequencies with high amplitude. So basically what I'm saying here is that we can look at the patterns of the black bars to tell us which consonants or which sounds we're looking at. So computers can figure out which sounds someone is speaking by taking a look at this data. So it can look at this pattern here. Let me use a red color. It can look at this pattern here and say, okay, this is the vowel E, E. It knows what that pattern is in terms of, say, an English speaker. Or it can take a look at this pattern here, which is much darker overall in different spots, and it knows that's the vowel ah, ah. What you also notice here is that the vowels are much darker than the consonants, and that's because vowels have free airflow. So we can hold ah, e, we get a lot of vibration there. So we get that consistent airflow with air pressure, so we get darker frequencies in other places. While j, s, b, sh, you know, when we had a buh, 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 we're holding air back. So we're not really going to get much of a waveform while we're holding air back. So that's why in this area, we're not producing any sound. So we're not really getting much of a frequency here. We're not really getting those dark bars. So this is how we can represent sound on computers. So we get waveforms and we convert these into spectrograms. So we have information about intensity stored, pitch stored, and then we can convert that to understand sounds. So this is how a computer roughly does it. And this is a very simplified pictures of how computers do it. In terms of, well, we'll talk about text-to-speech. What I want to actually show you is how this program works in real time, because we can do that. So I have a program called Prot, and this program is free to download. So what we can do is we can record, like, say, any word that we want. So I'm just going to record a quick sentence here. I went out last night. Okay, I'll save that to my list. And now I can view and edit this sound. So let's take a look at what.
We can't really see the screen. Sorry.
Yeah, I gotta put it on. Once it comes up, this one, there it is. Okay. So here is. So you can see the sound wave now, right? Okay, so I should be able to play back this sound. I think this is the sentence, I went out last night. I just said it. My memory, okay. Play. It's not playing, that's okay. But I went out last night. So here's where I said I went out last night. So we can see some of the frequencies here. We can see the waveform above. And what I can do is I can track, say, the pitch. So I can show the pitch. So I went out last night. Oh, here we go. Why did it play there? That's so weird. So I can show the pitch with the little blue bars there. I went out last night, so we can see some high pitch, low pitch there. We can show the intensity here. So yeah, it's going to be a little bit blurry because it's stretched out. We can see the intensity. So went out last is going to be a little bit louder than everything else. I went out last night. It's not quite easy to just have it determine what sounds it is. We need to use a different program to get the specific sounds out. But these free programs can even show me the different formats. So this is something that we haven't seen yet. But when I said that the little black bars show different intensities, this is the information that shows like the different intensities of each sound. So this is what the computer is using to determine which sounds are which. So where the black bars are strongest. So we can look at the patterns of these little red dots in a line and say, okay, when we have a dot here, 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 and here, it's probably this sound. When we have a dot here, 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 and here, it's probably this sound, and so on. So this is essentially what a computer is doing to figure out sounds. So I just wanted to show that to you because it's a pretty neat thing. And if you take a course in linguistics like LING 330 phonetics, you actually work quite a lot with this program called Prot, which I'll type in the chat. It's free to download and mess around with. And there's a lot of different scripts you can do with coding and have it automatically extract specific information for you. It's quite a powerful tool. But yeah, it's just a neat little program. So our guest speaker is going to talk a little bit about how we can take speech sounds and get text out of it. So I'm not going to cover that. But what I am going to talk about is a very basic system for text to speech. So I'm sure you've all heard those wonderful programs like Microsoft SAM, where you get the text on a screen and then you have it read it out to you in Microsoft SAM's voice. I mean, when we're 12 years old, we all have it read like inappropriate words and stuff to us, and it's funny, right? Um, so there's sort of a basic process that happens. First, we give it a text input. So usually we give it a sentence like, it's time for lunch or something. What happens then is that the computer needs to make a prediction. It needs to figure out what sounds these letters are going to make. It also needs to figure out what the prosody is supposed to be. So sounds, by prosody, what I mean is like it needs to figure out pitch, it needs to figure out intensity. And this is not an easy task. So what it's doing in this case is a lot of probability behind the scenes. So this is why we're not taking a look at an in-depth look of how it's done. There's a lot of probability going behind the scenes. And in some cases, it's even doing category parsing. It's determining the category of each word. It's determining sentence structure to figure out how this pitch and intensity should go for the sentence. Then what it's doing is it's converting all those individual sounds into a spectrogram. So it's taking each of those sounds and it's merging it together into a spectrogram. So once it has that spectrogram, so once it's gone through the prediction stage, it goes through what's called a vocoding stage. So the vocoding stage just takes a spectrogram and then converts it to a waveform through this thing called a vocoder. So we won't go too much into the details of what a vocoder is. We can just think of it as like this thing that takes a spectrogram into a waveform. And then that is what produces the voice. So that's how you get from text to Microsoft SAM. So if you go to like any website, I think even a Microsoft Word, you can right click on text and you can just say, read it out loud for me. And then you can have Microsoft's default voice read out your text to you, which, by the way, is a fantastic way to check for grammar mistakes in essays, because when you listen to anyone else read out your stuff, especially a computer, it's very easy to pick out grammar mistakes because the computer is doing its best to make predictions about how your sentence is supposed to be structured. And when the computer makes a false prediction and the sentence structure comes out weird, you notice it, especially when something is already kind of weird with the computer being spoken. So it makes it seem simple having two steps: change words to spectrogram and change spectrogram into waveform. But this is a very difficult task with a lot of probabilities going on and a lot of small details. So one application is text-to-speech. Now, some cultures have taken this further than others. Some cultures have taken this to music. So this is my chance to talk about Vocaloid. I don't know how many of you have heard about these, but I'll put on one of the songs during the second break. So these are pretty popular in Japan. These are made up characters that sing using digital voices. So they're either using computer generated voices or they have singers that record voice samples and then people manipulate their voice samples using vocoding programs. So essentially you can manually put in words or sounds like S, E, O, Sh, Z, and so on. and you can manipulate the pitch, you can manipulate the intensity, you can manipulate the key, and you can create entire songs using someone else's voice or using a digital voice. So uh, these are used for a lot of artists who don't have access to singers or can't sing themselves. In other words, it's a way for pretty much anyone to make uh, music with vocal tracks. And these are so popular that they have concerts for these with like holograms. So they take the characters and they just project them on a screen, and then people go see them in concert. I've heard they're some of the best concerts in the world because they're always on time. Like if the concert starts at 7, like you never have to worry about a bus being late because I guess they can change immediately. The performers are never too drunk to go on stage. They never mess up their dance moves. It's all just pre-recorded. It's a great thing, apparently. So I'll play one of the videos during the breaks so you can listen to it. I will say they do not sound realistic. So the music is a turnoff for a lot of people. It's not my favorite. Some sound better than others. The ones that are very clearly digitalized don't sound good, and the ones 15 years ago sound way, way worse than the ones now. But some of the voices where you have people actually singing and then people manipulate those, they sound a little bit better. So here's sort of what the program looks like. And this just talks, the text just talks about how you can manipulate things like pitch and intensity and stuff. So it looks like a music program. So you can determine the key, you can determine the sounds. So some of them are in IPA, depending on which pack you use. Some of them are not. But you can place them in the key. You choose the sounds. You can choose the length of the vowels. You can choose the intensity and how they change. So you have a lot of customization over the voice. So it is just music production. Now, if you're only living in like an English speaking world and you've never heard of this, I don't blame you. And there's actually probably a linguistic reason for why this type of music is not popular in English. And that's because it doesn't sound great in English. Some people have attempted to make English Vocaloid songs before, and if you compare them to, say, Japanese Vocaloid, which is very popular, there is a huge difference in intelligibility. So, um, uh, in, let's figure, I just want to specifically write that English Vocaloid songs are not very intelligible. And this is a question I actually want you to think about, and we'll talk about this right now. Why do you think English Vocaloid or English digitized tracks with CC-VCC syllables, so very complicated syllables, aren't going to sound as intelligible as, say, Japanese Vocaloid songs, where Japanese only has like CV or V syllables, which are very simple syllables? And so you can sort of think about this in your head a little bit, but this really comes down to prediction, to changing that spectrogram into that waveform, to putting things like the phonology together, putting all of those consonants together, and making it sound human. So when we speak as English speakers and we put a bunch of consonants together, we put consonants and vowels together or syllables together, and we speak quickly, we do a lot of changes with our sounds for efficiency and so on. And because there are so many changes, if you want to make a really good sounding English Vocaloid song with computer music, you have to string it together with a way that takes all of that into consideration, which means you need to do a lot of work to make sure those patterns are represented in the music. Now, a lot of artists who make these songs in English do not take that into consideration because they're not trained linguists, right? They or they're not aware of that, or the packs just don't have that information available, or they need tweaking, or they need a singer to come in and record more clusters for them so they can manipulate. There's just not enough to work with to make it sound good. But in Japanese, if everything is just consonant, vowel, or just vowel, they don't need much to make it sound good because there's only so many combinations and they have all those combinations. The patterns are simpler to work with. So the patterns for English are just a lot more complicated to make sound good, so they're just not going to sound better than, say, Japanese. And that's probably why it hasn't taken off yet, because the system just isn't good enough yet to make English songs sound good. Is it possible because digitized voice moving through 3CCP combinations sound more like sliding than distinctive bits and pieces? Sliding than distinctive bits and pieces. I don't know if sliding, I think almost, I'm trying to interpret what you mean by sliding, because maybe that's not how I describe it in my head, but it sounds very choppy sometimes when you listen to English Vocaloid. It's like it's very abrupt, choppy consonant clusters that just don't sound natural. I'll try to find one of those in the break too if you're interested in an English song that I think is okay from what I've found. But you can hear a bit of a difference that just doesn't sound quite naturally English. Okay, so this is all I'm going to say about sounds. Are there any questions about how sounds are dealt with in computational linguistics? Okay, let's talk about some text prediction now. So we've all seen this, and we've all seen how much this has improved in the past. Well, I shouldn't say all of us, because some of you were maybe like 8 or 9 years old 10 years ago. But text prediction has changed quite a bit in the past 10 years. 10 years ago, you got some really weird results. Now text prediction is pretty good. So if you ask a question, I did this yesterday, I typed, is Meryl Streep? And then the first 3 results that came up were, is Meryl Streep married? Is Meryl Streep still alive? And is Meryl Streep in Mamma Mia 2? I was a bit surprised by the third one. So how does a computer do this? Well, usually what a computer does, again, is it makes use of probability. And it does this by looking at these things called n-grams. And to make this simple, an n-gram is just some number of words. So a number of words. And I'm looking at specific examples below to sort of illustrate this process. So let's say we have Meryl Streep, and we want to make a prediction about what you're going to want to type after you write the word Streep. So what a computer is going to do is it's going to take a look at like a database of everything that's ever been typed into the search bar after Streep. So it's going to look for the word Streep, and it's going to take a look at all the words that have come after. So it might say, okay, let's take a look at 2 grams. So bigrams. And this means I'm going to take a look at Streep and 1 word after Streep and look at pairs of words. So maybe there's a pair where someone types streeped and married. And maybe there's a pair where someone types streep and still. And maybe there's a pair where someone types streep and in. And what it's going to do is it's going to add up all cases. And it's going to do this very, very, very fast. Very, very fast. And it's basically going to give each one a probability. Like it's going to say, okay, there's like a 21% chance they want to type married after. There's like a 17% chance they want to type still after. There's like a 12% chance they want to type in after. And then what they'll do is in the search bar for text prediction, they'll just give you the list in order from top to bottom. So married comes first, still comes second, and in comes third. And then they just order the rest down. So they could say they want to look at 2 words, so bigrams. But they might want to say, well, maybe 2 words isn't enough. Maybe we want to take a look at 3 words at a time. So I want to take a look at streep and then 2 words after to see like what people want to type 2 words ahead. So these are called trigrams, so triplets of words. So maybe people type streep and then still alive. And this is like 16% of the time, and streep and in and mama, this is like 12% of the time. And then who knows what words come after that. And then they rank all of those. And they just give you to them, and then they just give you those in order. Now, it's usually the case like, well, which one do you pick? Do you do 2 grams or 2 grams or 3 grams? Like, how would you know which one you're doing? Well, it's going to depend. So 2 grams is going to be faster than 3 grams, which is going to be slower to check. So with 2 grams, you're basically just looking at one other word after, and you're going through all of those. With 3 grams, you're basically taking a look at 2 words after, so you're checking more things. So if you want to have a check that's really quick, you might use 2 grams. If you want something that's really slow, you use 3 grams. But you might get something that's less accurate if you use the faster method, and you might get something that's more accurate if you use the slower method. So you're kind of working at a trade-off here. Now, this isn't the most modern method of doing it. The more modern method is doing things a lot more abstractly than this. But for a lot of simpler systems that are not necessarily Google, this is still something that you can use. So kind of a trade-off in each. So actually, why don't we try this? Like, let's try a very, very simple version of this just to see how this works. So let's try it with I want new, and then we're going to see what the predicted text is. And we're going to see what the prediction is based on these sentences. So let's pretend that we're typing this into a search bar, and this is everything that has been searched before. This is like the information that the computer can draw from. So we're going to do this based on bigrams. So what we're going to do is we're going to take a look at the word new. And we're going to ask ourselves, what word comes after new? And based on the probability of which word comes after new most often, that's the word that we're going to predict that someone wants to type. So basically, we're going to take a look at the word after new in each of these sentences, and then we're going to tally them up. So that's many. So we'll find new in each of these. And then we'll take a look at the word that comes after. Okay. So those are all the times we have new, and now we're going to list our bigrams out. So we have new and bed. We have new and tire. Because computers aren't very smart, new entire and new entires are going to be different words. They don't know the difference, at least not at this stage. New and products, new products, new products, new beds. Ooh, there's a new in beds. New tires and new products. Okay, so we have our different diagrams, but we should probably write how many times each one occurs, so that way we can figure out the probabilities. So I see one new bed, one new tire, one new tires, one new products, two new products, three new products, four new products, one new beds, two new tires, and five new products. So by taking a look at all the different words that come directly after new, based on what we've seen, the text predictor is going to say that you probably want to type, I want new products. Now, if we look at this example and we think, well, if we did this with a real search engine and you typed, I want new, you're probably not going to want to type the word products. That's kind of weird. This is, I mean, this is a very specialized example. This is clearly like a bunch of different advertisements or a bunch of different people asking about advertisements or something. But this is kind of reminiscent, reminiscent. Sorry, I don't know how to spell that word. Reminiscent? Reminiscent. It is an E. Thank you. You're saving me. It's a word I've never spelled in text before. This is kind of reminiscent of personalized predictive text. So let's say you have your iPhone or your Android, your own personal cell phone, and you make your own predictive text all the time. You're typing the words that you type. Your phone personalizes your own predictive text, right? Eventually, you type something so frequently that your phone makes suggestions for you to type that word over and over because it records everything you say. It makes notes in its database of what you say, and it makes its own predictions. So it's sort of like adding in information, and then when you type something that's similar, it says, hey, you always say WTFOMG, GGGG. Do you want to type that? And then you say, yeah, thanks. I always type that. So it's sort of reminiscent of that. So why don't we take a 10-minute break and then we'll come back and do part of speech tagging afterwards. So if you have any questions, I'm happy to answer them during the break or immediately after. So I'll see you in 10 minutes and I'll put on a Vocaloid song for you to hear. So if you don't want to hear it, just mute. If you do want to hear it, feel free to watch a live concert. And kind of an unrelated note, but a lot of the Vocaloid songs are like subtitled by Spanish speakers on YouTube. There's just a huge Spanish community for Vocaloid. That's always surprised me. Is there echo? Okay. If there is, I would have no idea how to fix it, so that's a great thing. Anyways, were there any questions about anything before the break? Okay, so we're gonna talk about words now and sentences, and a lot of the stuff is still very probability based. So when we come to something that's probability, I'm just gonna say it's probability and then kind of move on from that so we can talk more about applications. So uh, part of speech tagging or POS tagging, which is part of speech, not the other POS, is a lot more specific than what we did at the beginning of the course. We did 5 different word categories, but um, computers will take a look very specifically at all the different parts of speech. So I just wanted to show you a chart with all the different parts of speech that computers would use. And it not only looks at words, but also other characters because it needs to distinguish words from characters because people type with pluses and stuff in a sentence as well. So it needs to know like what's a symbol compared to what other words are. And part of speech tagging is somewhat straightforward in some cases because there are some words like I, which is always going to be a pronoun. And that's easy. Whenever you see I, like the letter I on its own, that's capitalized, it's a pronoun. Easy, done. But some words like back or wrong are more difficult because they could be multiple different categories. So it's what's called a disambiguation task because some words have multiple different parts of speech. So the tagger has to figure out, well, which part of speech is it? So once again, probability. So here's an example. And here's a sentence at the top where I take the word wrong in 4 different forms, and each time the word wrong is a different part of speech. So I made a wrong by wrongly wronging him with wrong advice. So wrong as a noun, wrong as an adverb, wronging as a verb, and wrong as an adjective. Taggers are computers in this case. A part of speech tagging is what computers are doing. It can be verified by people, but we'll talk about what computers are doing. So, how a computer is going to tag words as nouns, adverbs, verbs, and so on is by using the same strategy as predictive text. It will take a look at the previous words, and based on the previous word that it looks at, it'll compile a list of the most likely word afterward, or the most likely category for that other word, and assign it a category. So, for example, let's say we see the article what category is most likely to follow the word or which categories are possible? Well, if we have a bunch of different, say, phrases here, a happy man, we have one case where we have an adjective right after. A dog, we have one case with a noun. A coward, one case with a noun. And a weird old thing, one case with an adjective. So if we just take a look at this, if we have really we're going to be looking at either an adjective or a noun right after. Those are going to be one of the 2 choices. So if we see something, or like if the computer is looking at and it's trying to figure out, okay, I have a word here. I don't like, who cares what the word is? But let's say that the computer has a choice between picking a verb or an adjective. Well, in this case, the computer can make a smart prediction and say, well, if it's after the word it shouldn't be a verb, it should be an adjective. So the computer can use probability based on how English language works to say that's probably going to be an adjective and make a good prediction. If we have information about parts of words, we can go into words as well, and we can say, what about words with, say, ly suffixes? If we see a word with an ly suffix, like say happily or lowly or quietly or quickly, what categories often come after that? Well, happily laughing, laughing is a V. Lowly person, oh, you could have a noun there, that's possible. Quietly sleeping, sleeping would be a verb. Quickly left, that would be a verb. So if you see an ly suffix, then you're probably going to have a verb or maybe a noun. So computers can use this information here to help make predictions about what word categories are going to be. And to make sure that a computer is making the right part of speech for certain words, not only can it go forwards when tagging, so it can not only go left to right and assign word categories, but then it can also go backwards through the sentence and do it again. So it can go forward, assign categories, and then start from the end and go backwards and do the same thing to make sure for sure that it got the best categories as accurate as possible. Now, it's going to make mistakes, and that's where people can come in and verify and alter the rules and alter the statistics and say, hey, you got it wrong. Like, we need to go in and fix some things, or say, if you encounter this thing, like, don't assign it this thing, or manually edit the probability so it doesn't happen as often. But these are some strategies that computers can use to tag parts of speech for specific words. So, I mean, humans can use more information, right? Humans can look at a word like person and think, oh, that's a thing in the world. Or sleeping, oh, that's an action. We can use that information. Uh, when a computer is looking in a sentence, all it has are these words. It might have meaning associated in like a dictionary entry, but it can't actually think about what it means in the real world. It just has, a bunch of zeros and ones in its background, right? So it needs these strategies, it needs probability. Now, there's a one step above this that's a little bit more difficult for computers, but it's the same idea. It's called named entity recognition. So, like, what's a named entity? It's just something that's like a proper name. So, um, yeah, proper names. So people's names, business names, location names, time names. So I have an example sentence here with one of each. So Stephanie, a person who works at IBM, an organization, took a vacation to the Sunshine Coast, a location in July, which is a time for a mental break from her tough job. Okay, so this is very similar, but it's a little bit harder because it's not always just a single word. Like, for example, Sunshine Coast is two words. So, how does the computer know that sunshine and coast go together? That's tough. And another thing is when it sees something like IBM or Stephanie or Sunshine Coast, how does it know whether it's a name? How does it know whether it's a location? How does it know whether it's an organization? This is another tough task. But again, this just comes down to the same principles as part of speech tagging, which is just part of probability. Just taking a look at the previous words and the following words, taking a look at corpus database and taking a list of all the things that come before and after, seeing what happens most often, and then making a prediction based off that. But in addition, you can supply these programs with some information ahead of time. So, for instance, you could supply it with a list of really like common names or common locations or common organizations ahead of time. So you could take like the 10,000 most common businesses names or months of the year or stuff. So that way it has a basis to start with. So this can make the task a little bit easier for these computational linguists. So, I mean, this is a simplification of it. We won't go into the details, of course. But at this point, these problems have just been reduced to be as simple as part of speech tagging is. And when I say simple, I mean simple for computational linguists. But the task is simple, the implementation is complex. Okay, so like, why is this all important? I mean, part of speech tagging is like the basis for pretty much every application that uses words. If computers could not tag words for part of speech, they would not be able to understand what you're saying. Because in order to construct a sentence, in order to determine the meaning of a word, in order to determine the meaning of a phrase or to understand what you're asking it, it needs to know the category of the word. Because how if it doesn't know whether something is a noun or a verb, it doesn't know what meaning to get. If it doesn't know what meaning to get, it doesn't know how to answer your question. So if we don't have part of speech tagging, we don't have search engines, we don't have chatbots, we don't have so many things that we interact with. So one big application is machine translation. So this is translating from one language to another. So of course, one of the big things that we use this for is media. And this is like sometimes just automatic. So Google has this amazing feature now where you can just open up a web page in any language and it'll automatically translate it to the language you want. Sometimes it's not great, but for the most part, you can understand everything on the page that you would want to understand. But it's also really useful for helping humans translate. So we know that these automatic translators are not perfect. And that's okay, because they still offer a really solid basis for humans to modify. So we can start with automatic translations and then humans can go in and fix errors. And that is way faster than starting from scratch. And it does translation by doing this thing called a sequence to sequence network. So basically, this just means that it starts with one thing, it does a step-by-step change, and it ends with a final result. Now modern methods use like this machine learning, so like deep learning, a lot of probability, but we're going to run through like a somewhat older algorithm for this, and it's still being used by some of the more primitive translation systems. So uh, let's show you an example of how this works, and then I'll show you on Google Translate how we know where systems fail. So here is how a sequence to sequence network works for English to Korean, or just really any language to any other language. And I've coded it from language 1 to language 2 in blue to purple. So a very basic step-by-step instruction for how computers translate sentences. We start with some sentence in a language. So let's take the sentence, Steve eats crispy bacon. The first thing it needs to do is translate or label all the parts of speech. So it needs to know that Steve is a proper name, eats is a verb, crispy is an adjective, and bacon is a noun. If things fail here, the translation is not going to work out. It needs to know this information because word order is important in a language. If it doesn't know the category of the words, it might not get the word order right. So it also needs to know how to do phrases. So it needs to know what the subject is, what the verb is, and what the object is. So in this case, the adjective and the noun, crispy bacon, do form an object. So we're not talking about how tree structures are made, but the computer does have to work with that as well. So once it has all the phrase information and word category information, then it makes changes. It converts the structure. So subject, verb, object in English is going to change to subject, object, verb in Korean. And then the word order is also going to get fleshed out. So the subject is the proper name, the object, the adjective, and the noun are the same in Korean, so same order, and then the verb is the verb. So we've essentially changed the order now. We translate the words from language 1 into language 2, piece by piece, and then we end up with the result in Korean. Now, in order to verify whether this is a good translation or a bad translation, you have to have a Korean speaker or some speaker of language to look at that and say this is good or bad. And if it's good, then the translation works. If it's bad, then something with the algorithm has gone wrong and it needs correcting. So the sentence was Steve eats crispy bacon. Do we have any Korean speakers here that can say that this sentence is good or bad? Or do we not have any Korean speakers here that could verify that? Because I don't know if this is perfect or not, but this is what Google Translate has said. So usually for really simple sentences, Google Translate is good. It's when sentences get more complicated and the syntax gets really complex where everything falls apart. So when I say like, what are the possible problems with this algorithm? What issues do you find with Google Translate and other online translators? Well, uh, first of all, I can kind of answer this for you. One, uh, when languages are not widely used, Google Translate kind of sucks. So Google Translate really prioritizes the widely used languages for feedback and prioritizes those. And two, many morphemes, subtleties are missed. So things like, oh, perfect, formality, uh, honorifics, things like that are missed. Perfect for the question. For languages with different levels of formality, is there a standard default that Google will go to? Well, let's just take a look at that. So let's add a window capture here. Let's take a look at Chrome. So last week we talked about Japanese, right? I will see Fred. And so sorry, let's use a Japanese name and let's zoom way in. So we said that whenever we had a proper name like this, we would add some sort of honorific to it, right? Well, we don't have an honorific. We don't have like a san there or a chan or anything like that. So we don't actually have the honorific being translated into Japanese here with Google Translate. So that part of the language is not being translated at all. But if you don't know anything about Japanese, then you wouldn't catch this, but this is the more formal version of Japanese in terms of verb conjugation. So it does default to a more polite version, but it is missing politeness on the name. So one way you can test a translation to see how well things translate is to translate a sentence into a language, like language X to language Y, and then take that language Y and translate it back to language X to see what happens. So for example, let's do English to Mandarin. Am I, hello? Okay, I'm just gonna type it because apparently oh, it's just Chinese, simplified. What am I doing? Yes, of course. The linguist in me just wants to type in the M for Mandarin, but it's the script. Okay, so you can tell me how bad this translation is. When I went to the store, I found my friend passed out from drinking too much last night. Okay, so my guess is that what I've typed in is not translated perfectly. That would be my guess. Can anyone verify that? Oh, it's good. It's good. That is surprising. It's good. It's a little weird. Okay, so I mean, it's probably not 100% perfect, but okay, I'm surprised. So let's take this sentence. So when I went to the store, I found my friend passed out from drinking too much last night. And let's just reverse that. Now, Okay. So converting it, it's not too bad. When I went to the store, I found that my friend passed out after drinking too much last night. Okay, that's not too bad. So let's try translating it from Chinese into Italian. And let's take this Italian translation, and then let's convert this back into English to see what happens when we run it through a couple languages. Oh, wow, this is amazing. It actually is working. Okay, this isn't what I expected at all. So actually, English to Italian to Chinese is pretty good. If we did something like to Afrikaans, to Tamil, and then back into English. Ah, here we go. Here we go. Here's languages that aren't as popular. Something has gone wrong here. When I went to the store, I found that my friend had died after drinking too much last night. So it turns out that passed out, there's something about the phrase passed out that has just been mistranslated. Something along the Afrikaans to Tamil to English pipeline. Something has gone wrong. It's been misinterpreted as passed away, probably. So, yeah, there's been some idiomatic problem here. The idiom has been misinterpreted or mistranslated somewhere along this pipeline. But this is a good way to test for problems with the translators as well. Anyways, sorry, that shocked me. I was expecting many more problems with that. But yeah, these translators are actually much better than they used to. So, but yeah, as we saw with Japanese, for instance, we saw the formality. Yeah, try Bing Translate. Google Translate's going to be much better than the other ones. You're right. But the passed out to died is actually a pretty good transition into word meanings. Oh, geez. Oh well, at least we got a good one. We got a good one where passed away or passed out goes to die. Uh, yeah. Translating metaphor and understanding idioms is just a challenging task for computers in general. So for it to not get that is is um is understandable. I'm actually more surprised that the English to Chinese to Italian and back pipeline worked as accurately as it did. It's very impressive now compared to how it was years and years ago. So these translators are also trying to understand meanings too. And as you can see with something like, I don't know, passed out, when you have a word like passed out, this is idiomatic, but it has one meaning. So as long as it understands the idiom, it gets the meaning. But there are some simple words in English, like bank and mouse, which in our heads, we always understand based on context what it means. But the words themselves have multiple meanings associated with them. So bank can have multiple meanings. Typically, it's like it's the money place. But it can also mean like the river bank, like the sloping mound, the place by water. A mouse can be the animal, or on the test with the mouse crash when I realized, oh, it can also be a computer mouse. So that can have two meanings as well. So we talk about each of these meanings in terms of senses. So we can talk about word senses. So we can say that the word bank has two senses, or mouse has two senses. And we'd say one sense of the mouse, which we call mouse one, would be like the rodent, and one sense of the mouse, which would be mouse two, would be like the computer mouse. And we can talk about relations between the senses. So like, are they antonyms? Are they synonyms? Are they hypernyms, meronyms, and so on? So I'm sure you've heard of terms like antonyms and synonyms. We'll cover those again. But terms like hypernyms and meronyms, you might not have heard of. So computers will make use of this too. So that way they can understand what you're asking. So synonyms are words that are identical in meaning. So this sometimes depends on the person, and it might not be completely identical. So nearly identical is also good enough for synonyms. So couch and sofa, vomit and throw up, car and automobile. I mean, this one is very near identical, since automobile and truck are somewhat synonymous, but truck and car aren't. Uh, Antonyms are things that are opposites. So long and short, big and small, dark and light. Uh, Hyponyms. Hyponyms are like relationships between specific and general. So the specific is a hyponym of the general. So for instance, car is a specific example of a vehicle. So car is a hyponym of vehicle. Dog is a specific example of an animal. So animal is general, dog is specific. So we say dog is a hyponym of animal. The last relation between senses is something called a meronym. And this isn't something that I see too often outside of linguistics, but a meronym is a part-whole relationship. So this is like when you have an object and then you take a part of that object. So like if you have a car, that's a car. A wheel is a part of a car. So the wheel is a meronym of a car. But if you have a face, an eye is a part of a face. So eye is a meronym of face. So eye is a part of a face. So these are the different relations between the senses. Now, why are these important? Well, this information is important for computers because when a computer is trying to determine the meaning of a word, usually when you say words in a sentence, the words are related to each other. So if it has to choose between one of the meanings, like you use the word mouse, it has to check all these different relations with other words in the sentence to see, is mouse a synonym, antonym, hyponym, or meronym of any of these other words? And depending on which sense it is, if there is a meronym relation, like for instance, if you say mouse and computer, well, then it's probably computer mouse, because mouse would be a meronym of computer if it's the clicky thing. If the word computer isn't in the sentence, then I don't know, maybe it could be a rodent. So having all these different relationships is important to help a computer understand which meaning or which sense of a word you're looking at. Sorry, are there any questions about these relationships before the next slide? Okay, so on the top right here, I have an example of the database WordNet. And WordNet is a database that a lot of computational linguists use that have a lot of meanings of words. And you can explore WordNet yourself. You just type it into Google. You can type in any word, and you can be taken on a long journey of all these hypernyms and different relations, and you can find other words from it. So, for instance, if you take a look on WordNet and you type in mouse, you can see there's actually 4 definitions of mouse. And if you click on mouse, so I clicked on computer mouse, I saw that, okay, um, you could take a look at a meronym of mouse and you could find mouse button. And then you can take a look at hypernyms of mouse button. And you could also take a look at sister terms and so on. And you can go into a lot of detail here. WordNet also contains larger categories. So for each word, you know if it's an act, an animal, an artifact, a body, a feeling, food, plant, and so on. Just to have as much information as possible that a computer can draw from. So this is like a giant database of words, like a giant thesaurus that a computer can use to help analyze word meanings. So this is a very abstract picture of what it's doing. Basically, it's just using a lot of probability. So it's going through like all of the content words in a sentence. So I'm just going to zoom in. The text is just saying a lot of probability, basically. So let's say an electric guitar and bass player stand off to one side. So it's looking at all of these different words. And it's taking a look at all of these different definitions. So all of those, I'm going to stop circling them because it's just messing up the page. And it knows one of them for sure. It knows guitar. Guitar only has one meaning. And what it's doing is it's finding similarities between these words in order to determine the meaning. So for instance, player could be in-game, musician, actor, and so on. But it sees things like guitar, which is an instrument. It sees bass instrument. It's finding a connection between these. It sees player as musician. It knows there's a connection between instrument and musician, so it's picking that. Using electricity, this is a very high probability meaning. So it's connecting this to guitar and instrument. Relative region, side of body, slope, upright, bare, put upright. It's going through these and it's just listing them in order, the most likely, and making connections. So again, it makes use of these WordNet databases and a lot of probability behind the scenes to do this. So yeah, we just won't take a look at exactly how it's going on, but abstractly speaking, this is sort of what it's doing. It's taking a look at frequency data. It's taking a look at the senses and how they're compatible. It's taking a look at those super senses. So like, are they acts, instruments, feelings, emotions? They're looking at synonyms, hyponyms, baronyms, and so on. It's taking a look at all this information, putting it together, and then choosing the best meanings for each. And it needs to do this so that way, if you're asking it questions in Google or searching for things, it knows what to give you in terms of your search results. If you type in bass player, let's say you're typing in bass player into Google Images, and it shows you a picture of someone slapping two fish. That's probably not what you want. You're probably looking for a musical instrument, not the fish. So it needs to know what bass player means. Okay, so the rest of these are applications. Sentiment analysis, chatbots, and computer-assisted language learning. Because you'll explore computer-assisted language learning and chatbots, we don't need to spend too much time on those. They are very exploratory questions, but the information is in the slides. If we don't get to it, that's not a big deal. But sentiment analysis is incredibly interesting. This, to me, I feel like this is almost like modern day, and in the next 5 years, this is going to be very, very big in online moderation. In fact, it is pretty big in online moderation right now. So what sentiment analysis does is it uses all of this stuff with word tagging and word meaning and so on to determine whether a message is like positive, negative, real, fake, informative, uninformative, and so on by analyzing the sentiment of a message. So originally, this was done on like tweets to say like, is a tweet good or bad? Or is a comment on a news article good or bad? Uh, is someone making comments left-leaning or right-leaning politically? Like you can use it for that too. So for example, here's some review off of Amazon that is like greatly condensed. Now, take a look at the difference. Let's say that a parser is just looking at individual words, and we say, okay, some words are positive words and some words are negative words. And if it's a positive word, we say it's green. If it's a negative word, we say it's red. And if it's more green, it's good. If it's more red, it's bad. So let's say we have a system that looks at individual words. So these are just words. Okay, so here's the review. I did not like this product. Okay, like is a good word. It kind of works. Kind is a good word, but not really. It looks nice at first, but actually it's made cheaply and broke after one use. Well, nice is a good word. Cheaply is a good word. Broke is a bad word. I wasted my money on this. Well, wasted is kind of a bad word. But there's more good words than bad words. So if we used sentiment analysis with just individual words, okay, good review. This is what our sentiment analysis would say, because there's more good words than bad words. I mean, this is, if you read this review as a human, you're like, nah, this is not a good review. This doesn't sound good. So let's change our strategy a bit and let's analyze phrases instead. I did not like this product. Okay, did not like. That's a negative phrase. It kind of works, but not really. Okay, that's also a negative phrase. It looks nice at first. Okay, that's somewhat positive. It looks nice at first, but actually it's made cheaply and broke after one use. So made cheaply is pretty negative. I wasted my money on this. Okay, so actually, if we analyze this in terms of phrases and don't just look at individual words, this is a pretty bad review. So, I mean, which strategy is going to be more accurate? Looking at whether individual words are good or bad, or looking at entire phrases? Well, looking at entire phrases is going to be more accurate if we're trying to determine if something is positive or negative. But that's going to be a lot more difficult to do, looking at phrases to see if it's positive or negative. Why? Well, because with like part of speech tagging, if we know what the category of the word is and we know what the word means, we just have to say that's a good word or a bad word, and then we're done. If we have to take a look at phrases, the computer has to know how those phrases combine. It has to know the meanings of the words and how those meanings are changing the meanings of other words when they're put together. There's a lot more complex stuff going on that makes it much more difficult for a computer to do. So, how's it going to do it? And for phrases, the answer is it's a lot of stuff it's got to do. It's not easy. So, we're not going to take a look at how that's done. We're going to take a look at how the word stuff is done and how we can make the word stuff a little bit more complicated to make it a little bit more accurate, but still not perfect. So this is how we can determine whether a sentence is positive or negative using words. So how does it work? Colon, the simple way. So here's what a very basic sentiment analyzer is doing. Is for every word in the dictionary, it's going through, and this can be done manually by humans, or it can be done using statistics by computers based on other information given to it. You assign a word with a value between -5 and 5. And -5 is going to be very bad or very negative, and 5 is going to be very positive or good. So words like amazing, extraordinary are 5. And very negative words like horrible and broken would be -5. And then you have a bunch of neutral words. So words that are just like neither positive or negative. So words like is, by, some, dog, today, and words that when you hear them, there's no emotion that's evoked. I mean, you might hear a word dog and think, oh, that's good, but it's not like a positive or negative comment. So very basically, or very simply, what you could do is you could just list out all the words, add up all the values, and then get a score. So here's the dog. My dog, sorry, here's the dog. Here's the sentence. My dog is cute and sad today. So let's say cute gets a score of 3 and sad gets a score of -3, and all the words get a score of 0. So when we just add up all these numbers, what we end up with is a score of 0. So, okay, the sentiment analyzer would say, this is a neutral sentence. Okay, my dog is cute and sad today. Just a neutral sentence. Well, maybe that's not how we feel about the sentence. Maybe these aren't the best values. Maybe some of us think this is more negative than positive. Maybe some of us think this is more positive than negative. Maybe this needs adjustments. But this is what a very simple machine could do. We could also make this a little bit more complex by saying, well, what if we have a word like very or slightly and we intensify it? So we say things like very cute or slightly sad. And we could use these words to multiply numbers. So maybe very cute multiplies it by 1.5. So that's 4.5. And slightly multiplies it by a half. So it like downtones it. So that would be -1.5. So then the sentence, my dog is very cute and slightly sad today, this is just a more positive sentence in general because we're saying very cute. So very cute, we're intensifying the goodness, and we're saying slightly sad, so we're downplaying the negativity. So overall, this sentence is more positive than the last. So we could make that more complex. And if we want to take a look at phrases, maybe we could just do this more often with more words and make our rules more complex. But at a certain point, we'd have to rewrite the entire system to be a little bit more complicated or rely a lot more on just statistics overall. Are there any questions about how this works? So again, like we're just adding all these numbers together. Okay, so this can be used for automated moderation. And what this means is on websites, when there's thousands and thousands of comments per second, it's very difficult to manually remove things that are toxic or inflammatory, or just remove things that you don't want on your website. So with systems like this, you're able to analyze comments just without having any real person there. So here are real Amazon reviews. And not only can you do it for toxicity or positivity or negativity, but you can also use these systems to look at reviews that are real or fake. So, you could look at certain patterns in a sentence or certain words that bots use compared to what real people use. And when there's a certain threshold of real and fake words, you could remove it, for example. So I think both of these reviews are real. But if we take a look at the difference between a 5-star and a 1-star review, we do see a difference in sentence structure. We do see a little bit of a difference in the words that are used. So for instance, if we take a look at the sentiment of each of these reviews, just taking a look at the time, but I do want to show this. If we take a look at the words that are used, it's actually interesting. So in the 5-star review, we actually have negative words. like bland and putty texture. First, but these are definitely the best ones I tried. So actually, a lot of 5-star reviews out there that are written by real people will have negative words in them because they're comparing them to other products. While fake 5-star reviews often don't do that. Um, 1-star reviews are, they'll have a lot of negative words in them. So worst tasting, unhealthy protein bar on the market, that's a hyperbole. Threw the whole package in the garbage. If you want to eat healthy, these are not the bars to buy. Now they do have some contrast here. The brand Good Eats made in Canada are priced right, so they're comparing it and they're trying to sell a different product. So I mean, what's also interesting is that they could use sentiment also to take a look at the words and then apply a new star rating. So they could say, well, based on the language you've written, actually what you should be giving them is a 4-star. Actually, based on what the language you've written, you should be giving them a 2-star. So, should these systems be used like that? That's a different question entirely, but these are what the systems could be used for. Okay. So chatbots, things like Alexa, I'd give centaurs a good 4 out of 5. Yeah, very real. Chatbots, things like Alexa, Siri, Google Home, these are things that have conversations with humans to finish tasks. Um, there's different types of speech tasks that are used. So when people talk to others, they give like statements, they ask questions, they promise things, or they just acknowledge things. And depending on the type of statements you're making or the type of thing you're doing, type of speech act. So if you're asking a question, or if you're apologizing or greeting someone or making a claim, chatbots need to respond differently. So chatbots not only need to understand words and meanings, they need to understand the purpose of your speech. So even higher level, they need to know why you're saying what you're saying and what the purpose of your statement is. So when you wonder why a lot of these computer robots and computer like agents that talk to you don't sound like real humans, like why don't they sound real? It's because it's incredibly difficult to understand your intent. On top of all this other stuff we've talked about, just understanding what you're saying is difficult enough. Now they need to understand your intent. So they have constatives, directives, commissives, and acknowledgements. So these are the different types of things. I'll try to give an example for each. So constatives, it's like, uh, um, I don't think I want that. That could be disagreeing, advising, could you get me an appointment, promising, I will get to that soon. Uh, hello there. Like these could be different types of the speech acts. So I'm sure you've all had talks with Siri or Alexa or Google or other types of chatbots where you said something and they just have not responded appropriately, and you're just like trying to understand what went through the bot's mind, if it has one, and sometimes it's just it misinterpreted the speech act you're trying to make. There's one more thing that you need to know for the assignment. So I just want to get to that. Rule-based versus corpus-based chatbots. So just because there's one question on this. So rule-based chatbots just use rules. So you give it an input, and I tried to color code this. So like say you write, you hate me. And then it has these predetermined rules that says, if you give it this form, then it transforms the sentence into this frame and it outputs a sentence. So if you give it a noun, a verb, and a noun, it says, what makes noun think noun verbs noun? So this would say, what makes you think I hate you? And sometimes the rules just don't work. So actually, if you play with this, this is a bad rule. It works really only for this sentence, and it doesn't work for many other sentences. So you can kind of play with the different nouns here and see how that works. But a lot of rule-based chatbots just break down very quickly when you give it unexpected responses. Corpus-based chatbots, so corpus just means like a large database of sentences. They mine, so they search through human-to-human conversations from like these large databases and Wikipedia in order to produce real sentences. So they sound more like humans because they're basically learning from thousands and thousands and thousands of other conversations that are real in order to produce natural language. So chatbots are things that can talk with you online or over the phone, and corpus-based chatbots typically sound better than rule-based chatbots. So you'll look at Eliza and Cleverbot in the assignment, and you'll have to determine which one is which. Okay. The last 3 slides are on computer-assisted language learning, so this is about Duolingo. There's not really too much information. I will cover them at the very beginning of next week's lecture, but they're not completely necessary to finish the assignment. So if we hold off a week on those, that'll be okay for us. So I'll cover that next week, but we'll have a 10-minute break. And then when we come back, we'll have our guest speaker. So I will see you in 10 minutes. And the guest speaker will be recorded. So it'll be, I think, about a 20-30-minute presentation, and then 20 minutes for question and answers. So I'll see you then. For the first time in forever, I have turned off my program and have turned on my camera to introduce our guest speaker from Dialpad today. This is Vasundhara Gautam. They have graduated from SFU with a joint degree in Bachelor's of Computing Science and Linguistics a year ago, 2 years ago. I'll let you talk more about it. But they'll be talking about their work today. So feel free to take it away, and I think you can share your screen.
Cool beans. Let me do this. All right, I think you should see just the presentation and nothing else on my screen. My screen's a bit of a mess. I would have more space for things if I had both of my monitors, but I don't anymore because I am leaving Dialpad at the end of the month. And I'm going to move to Germany and do a PhD program in computer science. But yeah, I'm going to give you a short sort of guest lecture in computational linguistics, which is what I do and what I did my degree in. So I guess I've been in this space now for like 6 years. And my name is Vasundhara. I use ze, them, and they, them pronouns. I will talk a little bit more right at the end about my SFU journey, but for now, I kind of want to focus on speech recognition. And my sort of plan for today is kind of to give you an idea of some of the problems that we deal with in speech recognition, and to give you a high-level idea of how speech recognition works. And I think that you should have a lot of the tools to sort of understand that at a high level. At this point already, even though you're in Ling 100, which means you're just kind of getting a gentle introduction to linguistics. So I think I haven't been here for the last 2 hours, but based on what Trevor told me, I think that what you probably went through in the previous 2 hours were various applications of computational linguistics that were related to areas of linguistics that are not phonetics and phonology and not related to sound. So you probably saw things like Google Translate. I feel like you had a Duolingo thing probably. So translation, if you've ever used Siri, if you've ever had an interaction that was frustrating with a chat bot, or if you had something that was misdirected to your spam folder when it shouldn't have been, then you have to blame probably a computational linguist for that. Or they were probably involved somewhere in the process. So there's a lot of things that we use in our daily lives that are affected by computational linguists and by computational linguistics. Even though, you know, what the actual nature of a job in computational linguistics looks like can change. So my sort of sweet spot for what it looks like for me personally is when you have roughly 2 parts linguistics, 2 parts coding, and 1 part math. But there's a lot of different sort of things that you can do out there. You can lean more towards linguistics or more towards coding. You can honestly just build a career out of knowing very little about language and just knowing a lot about machine learning models and AI. Which I actually have a problem with, because I really think that you should know about language to do anything with language. But this is sort of my sweet spot. And I think over time I have, and, you know, in projects that I've done at Dialpad, I've kind of used all of my skills that I got from both the linguistics classes I took and the computer science classes that I took at SFU. So I'm guessing that most of you haven't done much linguistics, because this is like a 100 level course in linguistics. Although when I did Ling 100, I actually did it in my last term because it was a requirement that I just forgot about. And so I actually did it in my last term when I'd done like 400 level classes in linguistics, and I did it after that. But anyway, hopefully all of this stuff is at a good level for you and isn't like too basic, if there are any of you out there who've done more linguistics or more computer science. So like I said, I work at a company called Dialpad. It's your regular run-of-the-mill tech company that started in the Bay Area and has sort of spread around the world. It is technically, by definition, still a startup because we haven't gone public. But the company has been around for like 10 years, and we have offices in like multiple different countries, and we have nearly 1,000 employees. So it's rather large and rather well established. And what we do essentially is represented by 3 emoji, or at least this is how I'm going to explain it to you. What Dialpad builds is we build some different types of software to make calls. And so these calls can be like voice calls. They can also be video calls. And that's sort of the first emoji there, the phone. And then when you're on the call, what happens is, you know, you're speaking to another person or to multiple other people. And what happens is, as you're speaking live, we have speech recognition models that transcribe in real time what's being said. And you know, the transcript will show up on your screen. So that's the second emoji there. That's what I'm using. I'm using the sort of note taking to represent. And then the third emoji, which is the calendar, represents some work that a different team does called the NLP, or Natural Language Processing team. And what they do essentially is they take the text output of what my team in the middle generates, which is a transcript of the whole conversation. And then they use speech recognition, well, not speech recognition, but they use computational linguistics models, essentially computer models, to sort of extract the most important things out of those whatever conversation you just had. And so when you, let's say that you have a 30-minute conversation with someone, if you want to go back and sort of look at a quick summary of the conversation, you don't want to have to like go through 30 minutes worth of text. And if you promised someone that you would send them, I don't know, a document or something like that, you don't have to hunt to see when you said you'd send it to them by. And so what the NLP team does is they have a way of basically figuring out what is the most important information that people are going to want to look at afterwards. So for example, if you said something like, oh, I'll get you those slides by Friday evening, then what the NLP team does is they build models that will sort of highlight that at the end of your call, so that, you know, you can just kind of look at the highlights and you can put it into your calendar or whatever. You can just click a button and it'll add a reminder for you or whatever, stuff like that. That seems very fancy, and when it works, it's really cool. But obviously it's not perfect, otherwise we wouldn't have jobs. So that is kind of at a high level what Dialpad does. So we build a software. It's kind of like, it's just like your things that make voice calls, like your WhatsApp or your Signal or whatever, or that make video calls like Skype. And then you have this layer of AI on top and computational linguistics, where we do the transcription and we do various NLP things. Apologies for the siren outside. Anyway, so if you have any questions about this, if this doesn't make any sense, or if you have any questions in general, feel free to interrupt me in chat, and I'll answer your questions. And my next sort of thing that I want to go through is how speech recognition works. And then I think after that, I'm going to tell you a little bit about that, and then I'm going to ask you some questions, just sort of based on some words, to see what you think and what your intuitions are. And I'll use that to kind of highlight some of the problems that we face in our daily job. And then right at the end, I'll sort of tell you a bit about my SFU experience. And then honestly, it's not going to take like it's not going to take till 5:20 or anything like that. I'll probably be done by 5. And then I'll stick around if you have any questions that are like more specific afterwards. So with that, let's talk about how speech recognition works. And speech recognition, the way I define it here, is just a very high level. Someone's speaking, you have some audio, and then you want to convert it to text of like, what are the words that they said in English. And so, at my job, what we have and what we've been working on for the last few years is just English speech recognition. We're just now trying to expand to other languages as well. We're going to start with Spanish, and then we're going to look into possibly some other options as well. But for the purpose of this entire presentation, we're only going to deal with English. So what you have at the beginning to do speech recognition is obviously you need to have speech. You need to have some sort of audio representation of the speech. Typically, we use WAV files, so files with the .wav extension, because those keep a lot of information in them. We don't use MP3 files, for instance, because MP3 files lose a lot of information, and they're not as high quality, basically, and so it's harder to do speech recognition on low quality audio. And the picture that I have here is a waveform, which is just a visual representation of a sound. I feel like you've probably seen stuff like this before. I don't know if you've seen it necessarily in LING 100, but if you've ever like used, I don't know, if you've used like visualizations on like Windows Media Player or like iTunes or something like that, I'm sure iTunes has a visualizer. And if you've seen like how when the music plays, the kind of visualization changes, this is just another way of visualizing that essentially. And what I want you to notice is when you look at the waveform, you can see that there's like different sections of it that look like they're kind of separate. So you can see that there's stuff going on here. Like there's louder bits, there's softer bits where like the bars are very small. And then you can also see like in the first bit, the bars look kind of sparse. And then in the sort of second bit, there's like a lot of dense scribbling almost, it looks like. And so these happen to be actually different sounds that are put together, and they happen to be speech sounds. And so, just looking at this, you probably won't know what it says. You'd have to listen to the audio, but I'm going to show you, there's some more sort of tricks involved, I guess. So this sort of expanded version of the same thing that you saw before gives you a little bit more information. So the thing in the middle there, that's just below the waveform, is what's called a spectrogram. And a spectrogram is, again, just a different way of visualizing the same thing, which is sound. And it is something that if you go on to do more linguistics, if you do phonetics classes, you'll have to use this software called Prot. And you will deal a lot with these spectrograms, which are ways of just looking at different speech sounds. And for vowels in particular, if you look at those red bars that you see on the middle bit on the spectrogram, Those are called formants, and they can help you just look at a picture and identify what vowel is being said in that picture, just based on the pattern that the red bars have. And that's kind of cool because it means that you can literally just look at a picture and know what the sound is, which obviously wasn't possible when you just saw the waveform by itself. Now this is sort of tricky. I mean, I think like if you're a real phonetics nerd, then you'll have fun doing that, and you'll do it like just for fun, try and identify what's being said just from a visual image instead of listening to the sound. But typically, you don't really spend a whole lot of time in linguistics doing that, and nobody really needs to do that. You can just sort of listen to the audio and then annotate it. So that's what I've done in the third row there. I've essentially listened to the audio and segmented it into different speech sounds that make up this whole bit of speech. And I've annotated them with the International Phonetic Alphabet and basically given you what each sound is. So have you like done the IPA at all? Are you like vaguely familiar with it? You should tell me in chat. Some bits. Okay, so this is not like completely alien to you. That's good. So yeah, so I mean, I will read it out to you. I'm not going to like make you figure out what it is. Essentially, the sort of first sound there is I. The second sound, the one that's highlighted in yellow, is S. The third one is E. The fourth one is Y. And the fifth one is U. And so the whole thing, when you put it together, is something like I see you. And you probably have like a mental representation of what this utterance is. So keep that in mind because we're going to get back to it soon. So essentially, what I've done here is I've done some manual work, right? So I've gone in and I've used my Prot software program, and I have drawn the boundaries around these different sounds, and I have put labels on them and sort of used that to explain to you that different sounds are different and they look different and they just have different characteristics. So the part that I'm going to ask you to just like take my word for, because it would require like way more than a couple minutes to sort of explain. The part that I would like you to just trust me on is that you can teach a machine to do this. You can build computer models that will look at the audio and basically learn that a certain bit of audio that sounds like this and looks like this spectrogram corresponds to a particular sort of sound according to the IPA. And so when you do that, then it becomes fairly simple because you have immediately gone, if you've trained a computer model to do that and to do it fairly well, then you have a way of going from your audio in your wave file or whatever it is from someone speaking to a representation that is a sequence of IPA sounds. And so you have like a text representation because you have IPA symbols. So this is your next step. Let's say that you managed to successfully do that. You've trained your model. You don't exactly know how, but you have trained your sort of computer model to be able to do this. And so now you're not dealing with audio anymore. You can just throw away a wave file. And all you have to do, all you have to sort of deal with now is just a sequence of IPA sounds. And you have to figure out, okay, how do I go from IPA symbols to actual words and like sentences? So this is actually trickier than it might seem, because I would bet money that whatever you thought I said previously when I was reading out the whole sequence of phones, I bet that you didn't think that it was this, ICE and then EU. But that is a valid way of parsing this. It's entirely possible that the person who actually said the audio said ICE and then EU, like the European Union. Now, another possibility that I also think is very unlikely that you came up with the first time you heard me say this is icy, like cold, and then you, as in, you, a person. But again, it's the same sequence of phones. It's the same sequence of sounds. It just corresponds to different words, and you're kind of splitting them up differently. So the point that I'm trying to make here is essentially that it's not trivial to do this. It's not simple to go, even if the bit where you go from like a sound file to a sequence of IPA symbols is relatively simple, the next steps after that are not actually that simple. So I've made sort of a list of a few different possibilities that could have been the things that were said here. I'll read them out to you for fun. I see you, 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 and I see you. And I hope that by this point you realize that like all of them sound almost exactly the same. You could definitely imagine contexts where you don't really hear the gap between words, or that it's just so small that it's imperceptible, basically. They all kind of sound the same. And, you know, beyond a certain point, your speech recognition model is going to sort of struggle to distinguish between them. However, I would also say that it's probably extremely likely that when you heard me say the sequence of phones the first time, you thought that it was one of the middle two options, because those are just the most likely options. They're the ones that are going to come to your mind first. In fact, I would say that the third one is probably the one that most people thought of, even though the other ones are like theoretically correct possibilities. So what I would want essentially is I would want my model, my speech recognition model, to have some idea of like what is the most likely combination of words that people are likely to say in general conversation, even if it comes up with all of these possibilities, so that it can pick the most likely one. And you have to remember that sometimes this is contextual. So I would sort of say that if you look at all of the times you have said this sort of sequence of sounds in the past, it's most likely that most of the time, most of you would have been saying that third option. But I'm sure that some of you have mentioned like the intensive care unit in the context of like hospital conversations before, and you might even have said the other thing. So for example, I have said all of these other examples before in speech because I have made this presentation just now in front of you. And so clearly I have said that. So the sort of thing to remember is that you want your speech recognition model to have an idea for what is like, without any other context of the conversation or anything else, any context in the real world, you want your speech recognition model to remember to predict that third one, because it is generally just what is the most likely thing that people will say. But you also want it to be able to use context if it can. So for example, if you were to say, my friend was admitted to the ICU, it is pretty clear from that that you mean the fourth option. And so you would want your model to say, okay, admitted to the means that there's probably something that's coming after that that is a noun, and an ICU is a noun. And so as in the intensive care unit is a noun. And so let's pick that option. And so that's where, you know, using the context that you have allows you to kind of pick between various options that sound the same. And then they sort of help the model essentially generate a transcript that is as accurate as possible to what the person actually said. Even though, as you can see, there's a lot of opportunities for the model to just get bogged down and get the wrong prediction. So if you ever see mistakes happen, then you typically see mistakes like this, where things sound similar and maybe the model just like doesn't know a certain word or got the probabilities wrong, and thought that like a different option was higher probability than it should have been. So I'm just going to go through the same example again, but I want to highlight essentially the different sort of linguistics bits in it. Yes, I think my slide has changed at this point. And so essentially at every stage of this, there's different parts of linguistics that are involved. And you in Ling 100 have had like a really nice overview of all of these different sort of pieces of linguistics. So I'm hoping that all of these terms sound familiar to you. I will also try to define them just in case. So obviously in that first step, I already mentioned that you know, Prot is like a piece of software that's used in phonetics. And so, you know, phonetics and phonology, phonetics is like the study of sounds. Phonology is the study of like the smallest units of language. And in spoken languages, these are phonemes. And so essentially all of this stuff to do with like the little bits of sounds and like moving from an acoustic signal or a sound signal to symbols like in the IPA or in any other kind of phonetic alphabet, all of that has to do with phonetics and phonology. And those are the kind of skills that you would use if you're dealing with this side of speech recognition. The next step, where you kind of are going from, you have your pronunciation of whatever is sort of a sequence of words, and you're trying to figure out what are the words that are the possibilities for what was said in that moment. That uses a bunch of morphology, because morphology is like all about what words are, even though words are hard to define. And also uses things like lexicology and lexicography. So lexicography is like, essentially it has to do with maintaining a lexicon or like maintaining like a dictionary. So typically when you work on speech recognition, you have a list of all of the words that your model knows, or rather that your model is aware of. And you also typically have a list of pronunciations that are associated with each word. So it's what tells your model that the letters, you know, ICE is pronounced in English like ice. And so all of that sort of stuff that all of those pieces of information that go into your model to do that have to do with morphology and lexicology and lexicography. I don't think that SFU has any courses on lexicography, but I could be wrong. But I think that it gets touched on in morphology sometimes. And so that's sort of something to be aware of if you're planning to sort of do further classes in linguistics. And then finally, the last bit of like, okay, you've gotten from your IPA symbols 2 words, and now you're trying to pick what is the most likely sequence of words. You use a bunch of syntax, you use semantics, you use pragmatics, you use corpus linguistics. So syntax is how words are put together. So for example, you know, the third option there, that's ICU, is like a subject verb object sort of sentence, essentially. And so that is a likely thing that when you hear it on its own, it's probably likely that it's a full sentence with a verb in it, compared to some of the other ones where it's just like 3 nouns in a row. And so semantics is also kind of helpful. Semantics and pragmatics have to do with meaning and how language is used in context. And so sometimes you can use some stuff that's related to semantics and pragmatics to help you eliminate other options and to figure out like what's being said, essentially. And finally, corpus linguistics is essentially a kind of subfield of linguistics that uses huge amounts of data. So often it is text data. So it might be stuff that is like a lot of scraped tweets or a lot of scraped emails or a lot of, you know, just like text that is out there on the internet. And then corpus linguistics typically uses different ways of trying to look at patterns at a very large scale in a very large amount of data. So if you do that, then you can kind of get at some ideas like, okay, between all of these options in like a corpus of 7 million words, we found that the third option, I see you, was used, I don't know, 70,000 times compared to the other ones, which are all like either not there or just used like a few hundred times. So that's where corpus linguistics can help you. It can help you kind of figure out what is the most likely sequence and how do you kind of make it a higher probability that it appears than the other ones. So that's kind of what I had to say about that. And then now I have some questions for you. And you can like unmute if you want, or you can like tell me in chat or whatever. But I guess here is an abundance of Catherines, like the John Green book that I've never read. I want you to tell me what is similar about all of these and what is different about all of these words that I've listed in a row. And there's really no wrong answers. And all of this is meant to be very softball. Like I'm not trying to trick you or anything like that. So tell me what's common and what's different between these words. IP is similar, if not same, unless dialects get involved. Yeah, that was kind of the similarity that I had hoped that you would pick up on. The way I say all of these names, and I think the way that most people say all of these names, they're pronounced exactly the same. Can anyone tell me what is different between these sort of 5 words? It's not meant to be a trick question, I swear. exactly. The spelling is different for all of these 5. So what that means is, and I guess the problem that I'm getting at in the context of speech recognition here is, so they all sound the same, which means that, like I told you earlier, you're going to end up with, when something is pronounced exactly the same, you're going to end up with all of these options to choose from, but they all have different spellings. And so what that means essentially is that you don't really have a good way of picking between them. And this would be easier to do if they were functionally different, like if one was a noun and one was a verb and something like that. But all of these are names. And so they kind of appear in the same context. Typically, like you would say, my name is Catherine, and you would have no idea which spelling that is. So your model just has to guess at it essentially until it has further information. And so yeah, so anyway, so that's sort of the thing that I was getting at. That makes it hard. That makes it essentially so that speech recognition is not like a truly solvable problem, because there's always going to be missing information. You always have to make a best effort. And this applies not just if you have like a speech recognition model, it also applies if you're a human. Like if you just hear someone say that my name is Catherine, you don't really know how that's spelled. And so if you were asked to transcribe that conversation, you would just have to pick something almost at random. Of course, in our case, we don't do it at random. We try to pick the statistically most likely one. And it turns out that of all of those 5 options that I've listed there, the first one is the most common one by like a pretty large margin, according to census data in the US. So anyway, that's that. Let's do a couple more. Here are 3 words. Tell me what is similar, what's different, and you know, I mean, any observations that you have about these 3 words, tell me in chat. And again, none of this is meant to be a trick question, I promise. Yeah, exactly. Yeah. So so some of you have picked up on the fact that the I's sort of ending in British English is spelled with an S, and in sort of US English it's spelled with a Z. The first syllable is the same for them all, correct? I mean, so they're kind of all pronounced almost the same. Obviously there's some accent differences, but really the difference that is kind of important here, and the other thing is like the O versus the OU. The differences are all kind of spelling differences that are to do with regional differences in what people expect to see. So if you were to transcribe, if you had a speech recognition model that transcribed any of these 3 words when I say the word glamorize, it's technically correct. It's not wrong. All of these 3 words and these 3 spellings of the same word essentially are valid according to various dictionaries that you look at. So you're not technically wrong. However, when you have a speech recognition, when you have a user who is like British and in Britain and uses some sort of speech recognition software, and then it gives that person the first option, they might be pissed about it. We have definitely at Dialpad had feedback where people like, do any models shorten these words with multiple spellings for safety? Interesting. No, we typically don't do that. So we typically don't do that because then it's ambiguous. Like if someone said Kath, and if they said Catherine, but if you transcribe both those versions as Kath, that's dangerous. So we try to be as true to like what was actually said as we possibly can. And so I'm sure that there are models or there are companies that take a different approach and that exist out there, but I think most of the ones at least the ones that we build and all of the companies that we benchmark our code against. So I think we try out software from various other places, including like Google and Amazon. They don't do that either. And so anyway, the point that I'm getting at is essentially you don't want to surprise your users by giving them a spelling that they hate. And there's very sort of nationalistic things associated with this as well that we won't get into. but that is a concern sometimes. So here I have another example. Does anyone want to tell me if this is challenging for speech recognition or not challenging? And if so, why? Do you have any thoughts on these two words? Yeah, so someone says, I think the context around the words would make it easier. Yeah, and that's a really good observation. With tagging maybe easier, but alone difficult. So yeah, so the example that I want to show you, or the context that I want to show you, and this is of course a cherry-picked example, but it does support the sort of argument that like context makes it easier. So for example, if I said they are dash years old, what would you put in there of these two options? And if I had the next sentence, which says like, I dash too much at dinner, what is the most likely thing you're going to pick? It's like it's fairly obvious that you would pick the first one for the first option for the first sentence. You'd pick the second one for the for the second sentence. And so so when your speech recognition model has context, and especially when it can go back and like fix previous errors, which a lot of our models can, then even if their first guess is wrong, just by probability, then it can go back and like fix the error later because it has more context. Like let's say that 8 is just a more, like the number 8 is more common than the verb 8. Then without any context, your model might predict the first one, that is the number. But then if you say 8 too much at dinner, if it could go back and be like, okay, well, clearly that's not the right context for that, and it could change that, then you get like a better transcript overall. So that is that. And then I have one final example. Trevor has a question. What's the preference for pun translation? Because even -9. Interesting. Well, I don't know. I would have to check my model to tell you, right? Because 7, 8, 9, and you don't know which spelling it is. I feel like it really depends on whether your language model happens to know that joke or not, whether it's been fed as training data to the model or not. But I think it's theoretically possible that it would know to use the verb and not the number. Although I feel like in the case of the pun, it doesn't really matter because you use your mind to like translate it and to get the joke. So I feel like it doesn't really matter in the case of the pun. So yeah, so this is my final example. I have 2 words up here. Tell me in chat, what do you think about these words? Do you think about them at all? Do you have any thoughts on the similarities and differences? And you may not have actually seen the first one before. So if I don't get any responses to this, I will sort of tell you, and that's fine. But I'm hoping that I get lucky. Oh, has it not? Oh dear. Okay, I guess it hasn't. There, did that change it? Yeah. So any thoughts on the differences between word 1 and 2? I have some things in the chat, something that says A. So does that mean that you think that it's a pronunciation difference? Okay. So yeah, they're both pronounced differently. The first one is I, exactly. And the second one is typically, and it's again, it's the same letters, it's just capitalized differently, but when you read that, you typically read it as AI. And so if you're saying stuff in real life and you're seeing a transcription, you would expect the transcription to get the capitalization right based on what you actually said. And also, I don't know if you know this, but the word I is another word for, I think it's called like a white-throated sloth or something like that, a white-necked sloth, something like that. It's a type of sloth, essentially. It's very cute. And this one, I also want to show you that the pronunciation is different, right? In both of these cases, which is nice, because you can form sentences where it is ambiguous what you're saying if you have the text alone without any capitalization information. So if I were to say that's a cute eye, then I'm talking about the sloth because I said I. But if I say that's a cute AI, then I'm probably talking about like a cute robot that I saw and that I don't know, that I played with. And then, similarly, you can build another sentence like that dash scares me, where you can talk about a sloth scaring you, like that eye scares me. And you can also talk about an AI being scary, like a robot that's like terrifying, like the Boston Dynamics robots. So anyway, so that was my point. I'm glad that you all participated and had thoughts on that. And I'm just going to like very quickly breeze through my 4 years at SFU. In my first year, I settled in. I had just moved here from North Vancouver. And so I had like various intro classes. I worked at the dining hall. I was on the meal plan. I was on residence, blah, blah, blah. My first year was fairly uneventful. My second year was fun. I started working at the phonological processing lab. The logo is up there. The logo was designed by my best friend, whom I now live with. And so that was fun. That's a throwback. And then there's a bunch of pictures of like when we went and saw Arrival in theaters, because that's like the linguist movie. And various other pictures associated with the lab and my classes in second year. In third year, I actually didn't do any school at all. I did an internship at GE, which is where sort of all the pictures are from. I did that for 8 months, and then I took 4 months off and just like went to India and like hung out. And so didn't do any school for third year, which was fine because I did a lot of classes in the summer and stuff before that. And then my fourth year, I did a different research assistantship at the discourse processing lab. And again, I have some pictures. I did like a poster. I did like a presentation at the undergrad research symposium, got a publication out of some other research. And then I graduated. So I guess my graduation picture with my advisor, Maite Taboada, is at the bottom right. So those were my 4 years. I did that at SFU, and then I started working at Dialpad. I was hired as a computational linguist. And then a year later, they were like, we're going to normalize all of your titles because HR wants us to. And so I became...
See, I changed my name.
What? Was that an accident? Maybe that was an accident. But yeah, so essentially, so then they changed our titles, and I became a speech recognition engineer. I do the same job. It's no functional difference to my job at all. But yeah, so that is my story. And I guess if you have questions, you can ask them now, or you can also go to my website, which I will also type in the chat. And there's various like contact methods for me out there. So if you ever have any questions about computational linguistics or any of that, you can always reach out to me. So yeah, any questions? It's all good. Very good question. So the question is, are there any speech processing models that can accommodate code switching between two languages? If so, how does it handle intersentential switching? So I guess, I don't know, does everybody here know what code switching is? It's when you combine different languages together in speech. Sometimes they can be full sentences. Sometimes you can have intrasentential switching. So you have like words that switch over or little phrases that switch over, but the sentence itself is composed of different languages. So yes, there are models that do this. It's not very common, but in fact, the work that we're doing on Spanish does have to necessarily allow for some amount of code switching, because we're building a speech recognition model for Spanish spoken in the US by like US speakers. And so that sort of just historically has always involved some sort of mix of various things. There's a lot of concerns that sort of go into this. So one thing that's necessary is you need to, in your lexicon, that is in your dictionary of words, you need to have words that are both English and Spanish for this case, which I'm going to use as an example. Otherwise, your model just doesn't have any chance of ever predicting a word if it doesn't know it. So you have to make sure that you keep track of both. Another complication is in some cases you might have multiple variants of like something that means the same thing. So again, in the case of like English and Spanish, you have New York in English, and then you have like Nueva York in Spanish. And so you would have to have both of those versions in your lexicon. You'd have to have various different pronunciations. In some cases, the speakers might choose to just say it like with the sort of US English pronunciation, and in other cases they might do it with more of like a Spanish pronunciation. And then the other sort of aspect that you have to deal with is you have to have like language modeling for this intra-sentential switching. So essentially what that means is, you know how earlier I was showing you that you have all of these different options that sound the same, but you have to pick the most probable one. You have to have more data to be able to say that this version of a certain sentence is more probable than a different version of the sentence. And especially it obviously gets complicated when you have more words and more languages to choose from in all of your options, because you just have like a lot more options to choose from. But essentially, if you don't have the data to make that decision, then it becomes hard. So yeah, the answer is essentially yes, models exist, but it's a very hard problem, and there's a lot of things that you have to consider and deal with, and you need a lot of very specific data that is not always available. So any other questions? Any follow-up questions on this one? Is that processing models for animal sounds? So good question. So it's not what I work on, but I know that this exists. I'm going to try and find a link. There's a Merlin bird ID app that's made, I think, by the Cornell Lab of Ornithology. And essentially it's an app that helps you identify birds. And I think they recently added a feature where the app has like some built-in AI that will allow you to listen to bird song, and like it will identify what the bird is. And I've heard a lot of good things about it. I haven't actually had a chance to use it myself, but I'm very into birding, and I have a lot of friends who are birders as well. And so they have said that like it's really incredibly good at identifying different birds just by their bird song. And so, of course, birdsong is not, I guess, the same as like animal sounds, but it's a subclass of it. And it's actually pretty cool that it does that, because often you'll have birdsong that sounds quite similar to a different bird, but like you have to be an expert to be able to distinguish them. And the app can do that. So that's pretty cool.
So it's a different type of tweet analyzer.
Exactly. That was funny.
So for some people who might want to get into computational linguistics but don't know where to start,
yeah,
what's the best place for them?
Okay, you're literally at SFU, go take CMPT 120. Or, you know, in my time it was 120, but that was 6 years ago. So I don't know, go look at the computer science website. There's 100 level courses that exist regardless of whether you have had any previous programming experience or not. I should also clarify, when I started university, I decided that I wanted to do computational linguistics and I wanted to do this joint major program, but I had never done linguistics before and I did not know how to program. And so I literally like moved here September 2015 and I was like, I'm going to do computer science and linguistics. And I had no fucking idea what I was doing. I don't know if I'm allowed to swear in your class, but I just did. And anyway, so anyway, I would advise you to just do it. It may not be a GPA booster, whatever, but it's like super fun. And I mean, I really got into it. I really got into both things. I really like programming. I really like linguistics. They're really fun, especially if you like solving puzzles and like finding patterns and things, then both are really nice. They're slightly different versions of, in my opinion, the same thing. Are there specific 300 level CMPT courses that are applicable towards computational linguistics? Yes, I can think of two. There's one that is called, I think it's called like artificial intelligence. I think it's CMPT 300. Oh yeah, 310, exactly. So CMPT 310 is, I think, called artificial intelligence. That one was a good one. And then another one was, shucks, I have to like remember what classes I took. There was one that I did that was, well, so there was one CMPT course that I did that was like computational data science. I think it might be CMPT 318. That's a good one. And then there's CMPT 413 as well. Oh, maybe it got made into a permanent course. That's right. Yeah, because I think when I took it, it was a special topics course. So sure, that's the one probably. I did it with Greg Baker, who's really amazing. Definitely do CMPT 413 if you can. It's not offered super often, but it's natural language processing with Anup Sarkar. He's the one who always teaches it. And then there's also the compilers class. So the compilers class is something that you can either take that or you can take LING 400. And they're kind of like the linguistics versus the CS side of the same coin. So those are both really good classes, very related to linguistics. Blair asks, there's a LING 250 course that was introduced last year that teaches Python. Is this program widely used in comping? Yes, I code in Python basically all the time. Python is my #1 language at work. The other language so the main programming languages that I use, which I will just sort of put here in chat, are Python, Bash, and C++. If you intend to become a linguistics heavy computational linguist, you will definitely need Python. They teach a lot of R in school, but R is typically not used in industry. So it's useful to know just as a programming language and to do research and stuff. It's definitely used way more in academia than it is in industry. And Bash is definitely a good language. You don't really need to know C++ unless you plan to get more into computer sciencey stuff. But of course, like I said, I have a joint major in computer science and linguistics. So of course I did a lot of C and C++ and Java and stuff like that in school. Yeah, I guess we're at 5:20. I shouldn't like hold you.
No, thanks a lot for the presentation. That was very informative and a
Cool.
really good summary of like, well, basically showing that everything we talked about today in the first 2 hours is still relevant in the field, and that
Amazing.
yeah, so it's a very valuable job. So
thank you for validating me, Trevor.
so.
Yeah, I'm very happy to be here, and I guess I'm still sharing my screen. Yeah, like if you have more questions, if you want to reach out, even if you just like want to be friends or whatever, you can do that. If you don't have like important questions to ask me or anything like that, that's fine. So yeah, I will look forward to hopefully hearing from some of you. And yeah, thanks for having me, Trevor.
Yeah, no problem. You can follow them on Twitter and all that stuff. Check out their website. The website is linked in the announcement post for this lecture as well. So you can check out the website there. And for everyone else, that's it for this lecture. So as always, bug me over email, discussion board and everything. The exercise will be available tomorrow, and I'll see you all next week. So thanks for coming out and enjoy the rest of your week.
Cool beans. Bye, everyone.
Bye.